Thing is, the first question it asks is, so we're just going to do the second page. Everyone did pretty well except for the list of 5 basic things of the waveform, and that was on that sheet that I gave you. So everyone should have gotten that. But we're going to just take a look at calculating the sine wave here. So the first question it asks for is, what's the wave shape?
Sine.
Yeah. Or what's another name for a sine wave there, Jake? That one was good. That one was good.
You put it round and erased it.
I erased it.
Yeah, did you?
I told you.
It is a circle. It is a circle without time. It is a circle without time. So, yeah. Okay. So our first step is that we have to. So we identified that it was a sine wave, and then we have to. Our second one is that we want to identify what the period is. And it doesn't really matter where you go from. So for example, here we said that this is our zero reference, right? So we could have gone from here and then go up, down, and then right when it starts to repeat itself, and go right to there again. Okay, so if we did it that way, so here this one ended up landing right on the line, so we'll just make it easier on ourselves. So the first thing you want to do is just start counting how many divisions that one complete waveform is taking. So you're just going to go 1, 2, 3, 4, 5, 6, and it's a little bit over 6, and we have how many divisions here? So we have 1, 2, 3, 4. So each division is going to be worth what?
0.2.
0.2. So what I do is I just take my 6.2 divisions. That's how many divisions I counted, and then you're going to multiply it by how much each one division is equal to. So you should get 6.2 times 500 nanoseconds. So if I take 6.2 times 500 nanoseconds, what do I get for a period?
3.1 microseconds.
3. What?
1.
3.1 microseconds?
Mm-hmm.
So your period should have been 3.1 microseconds. And then if I do the inverse of that, then I get what for the frequency? 300 what? 22.
0.6.
0.6 kilohertz. Okay. So that's how you want to calculate out your period. Okay. So it doesn't really matter where you go. You can go, you can go from here, to one complete waveform. You could go from your peak, to your peak to peak, but I kind of look for I typically kind of like to stay right where my zero is. I kind of use that a lot of times. Where's my 0 volts? And where is it crossing over my 0 volts? And then when you're doing that, then you also will realize that my 0 volts here, then I already know that I'm going to have some kind of a DC offset on there because I don't half my voltage peak isn't right above it, and half my peak is not right below it, so I know I have some type of a DC offset in there. Alright, so then our next one is that we want to calculate out what our Vmax is. So we already said that this is my 0 volts. Now if you had your oscilloscope, you can use your horizontal position, you can kind of move it over so that you can get it on top of one of those divisions. But I kind of made it so that we can kind of see that it isn't quite on the one division. But we are about right there. So what you want to do is, again, you want to start out from your 0. Everything is referenced off of where that 0 volts is. So you're going to start out from your 0 volts and you're going to count out these divisions. So I'm less than 1 division, so then this time I got 3 subdivisions, so each subdivision is going to be equal to what?
0.25.
0.25. So then I'm going to have 0.25, 0.5, 0.75. So then my Vmax then is going to be equal to my 0.75 times what?
2 volts.
My 2 volts. And if I multiply it by my 2 volts, I'm going to get 1.5. Now am I above or below my DC reference?
You're above.
I'm above, so that's going to make my 1.5 positive or negative?
Positive.
Positive. You got to make sure you get those polarities on the Vmax and the Vmin. Alright, so now we got our Vmax. Then we're going to do the same thing with our Vmin. So our V min is coming right down to here. So again, you're going to start off from 0. Count down how many volt divisions you have. I got 1, 2, 3, 4. So I got 4.75 this time. Multiply by my 2 volts again, and this time I get what for my V min?
Negative 9.5 volts.
Negative 9.5 volts. Okay? So then, so now we got our V max, and we got our V min, we got our polarities on there. Then we just need to figure out what our voltage peak is. Well, my voltage peak is going to be from, so the easiest way I do it, I go from what's my voltage peak to peak first. So I know what the potential difference is between my V max and my V min is. That's going to be my voltage peak. So how much of a difference in voltage do I have here? Not adding and subtracting, but what is my difference between these two numbers? 11 volts. So that means that I'm going to have 11 volts peak to peak. Then to go back up one and then calculate out what my voltage peak is, I'm just going to divide this by 2 and I get what? 5.5 volts peak. Alright. Then we just have to figure out our voltage DC. This is where, this is one that you have to kind of, formulas in the book for V max, well, we can kind of manipulate that formula around. So we know that on wherever my DC offset is, I know that half my voltage peak is going to be right above it, and half my voltage peak is going to be right below it, wherever that DC reference is. So we know that we have a 5.5 volts peak. So what I'm going to just do is I'm just going to take my V max, look at what my V max is, and then I'm just going to go ahead and I'm going to just subtract my voltage peak from that. So my V max was one positive 1.5 volts, and subtract a negative 5.5 volts peak from that. And what am I going to get? 4 volts. So then so I know that here's 0. Then I'm just going to count down. 1, 2, 3. Let's see what happens. 2 volts per division. 1. So right here's my, because I got 2 volts per division, so I'm just going to count down. So my voltage DC is going to be right here. And then that's, so is that a negative 4 volts or a positive 4 volts?
Negative.
Yeah, negative 4 volts DC offset then. Now I know that I got half my voltage peak above it. Let's see, that's right.
It should be down one more.
Yeah, it should be
Gotta
down.
go down one more.
Yep.
Okay, so it's, all I see is pixels.
Yeah, that should be the one.
There we go. So here's where my negative 4 volts DC is. So here I have my voltage peak there. And I have my voltage peak there. And that's where and since I know that I got 2 volts per division, here's my 0. So I'm going to have 2 volts, negative 2 volts, negative 4 volts, and that's where that sine wave is going to be riding on, right on that, superimposed on top of a voltage. Okay? So, and I can do it the other way too if I want to just, I can take I can go the other way too, I can take my V min, and I can add my voltage peak to it. Either way, whichever way you want to go, you should be able to get your 4 volts. So I took my V min plus my voltage peak, because now this time I'm just going, here's my V min, and I'm going to add up my voltage peak to it. Now I'll bring up to where my negative 4 volts is, so either way. Okay? Alright, then our next one, I think a lot of people were getting this one, but it was, I think it was because they had everything else wrong. This is why I don't like some of these quizzes, because it's all based on if you did the first part of it right. But the instantaneous formula, so So we know that we have, so our instantaneous formula for 45 degrees, so our VINST is equal to my
VP
Well- times my sine of theta plus my voltage DC.
That's what I forgot.
Yep, so you got to make sure you add in that DC offset in there. So what I would just do is I take my 45 degrees, if I'm using one of these calculators here, for myself I would take 45 degrees, hit my sine key, multiply it by my voltage peak, and then whatever that answer is, then add my voltage DC offset to it. So on this one here, so I would take my 45, times it by, hit my 45, hit my sine, multiplied by my voltage peak, which was 5.5, and then I'm going to add in my DC offset plus a negative 4 volts. Should give you a 10.9 millivolts is what you should get. Okay? So that's what you should get. And that's all. So you know that at 45 degrees then, at 45 degrees, you're going to be somewhere really close to your 0 volts DC. You're just going to be slightly below it. That's where you put your dot. It's going to be right about that location. That's going to be about where your 45 degrees is. Your 45 degrees is actually not really halfway in between. It's kind of does end up being more towards the peak of your voltage. And then the very top is going to be your 90, and then your 135. So if you had another 45 degrees to that, your 135 would be here, and that would give you another negative 110.9 millivolts. Okay. And this one here is also too on that cheat sheet. So you should be able to, just make sure you look at that cheat sheet that I gave you for chapter 8 there. All right, any other questions on the quiz there? Yep. So it's just nice to know. We just need to know how to, we can take use those digital oscilloscopes, take those for, there's a lot of neat little functions on there, but there's just times where, right now, what we're working with is very basic signals and stuff like that. But when we get into a lot of the field and stuff, we're going to have to be analyzing very random type signals, especially when we get into noise. So, for example, here's a nice little sine wave. Well, we might end up with some. So here's our sine wave that we want. That might be coming out of our servo drive or something like that. But within this fundamental frequency, we might end up with another. I'm not going to really draw it the right way, but just so we can see it. There might be another frequency that's riding on top of that frequency. That's kind of our modulation. It can either be modulation or it could be noise, unwanted noise that's riding on our fundamental frequency. And so sometimes we have to, analyze what is that frequency. If we're trying to eliminate that noise, how can I get rid of that noise on there? Because I might do it with a filter or of an inductor or a capacitor or something like that, some type of a circuit to eliminate some of this noise. Or I might want to realize that it's what we call common mode noise, and we might want to, and when we get into op-amps, we can see how we can eliminate these signals going into an op-amp, and we can eliminate our common mode noise. And that common mode is really something that we run across when we're out in the field. So sometimes we have to be able to analyze it. The oscilloscope's not going to know what is it that we're really looking for. It might give us the frequency of the fundamental frequency, but we might want to be looking at what is the frequency of the noise. Another one that what I was working on right now was I had coming out of the turbo drive, I went into some transformers, came out of the transformers, then I went into a rectifier, so I was rectifying my AC signal, And I was expecting a nice clean DC with maybe a little bit of ripple because I didn't have any filters on it. So I was expecting, something to be about, nice and clean at a positive 12 volts DC. Well, then what I ended up with seeing was all of a sudden, every so often, I would get this. That's how my oscilloscope looked like. All of a sudden, I'd see these consistently. Always, what was this? All of a sudden, I would just see these little spikes in my DC voltage. And so I analyzed what that frequency was, and what I did is I took that one little part, this one little area, because I had more than one complete cycle. So I kind of took it and I kind of averaged it all out, took a look and see what one complete cycle was. So I really zoomed it in, so then I kind of, seen something like this, and I took my one complete cycle, found out what that frequency of it was, and I used my cursors. I went and I did my cursors, and I found out that this frequency here was at 6 kilohertz. Well, on a servo drive, on an AC servo drive, it's an AC signal, but then what they do is they have pulse width modulation within that. And that's our switching frequencies on our fundamental frequency. And that switching frequency was my 6 kilohertz. And so at that point then I knew it was my 6 kilohertz noise. And so then I had to figure out how I was going to eliminate that noise out of my DC voltage. And that time we did it with another transformer and grounded it up, an isolation transformer, and that eliminated that problem. So sometimes, we're analyzing a signal within the signal to find out what we need. That's why it's nice to be able to have cursors, know what one complete cycle is, so we can calculate out what our frequency is, and understand how we use that equipment for troubleshooting. That's typically that's when we dig out our oscilloscope, is when we start having troubles. And when we're having troubles, it's not going to be textbook signals. It's going to be some really ugly noise and stuff. We've got to be able to understand how to read it. If we have a hard time interpreting what we want to read, so does the oscilloscope. So that's why we need to know how to look at a signal and analyze it looking at the screen. All right. All right, let's get on with chapter 10 if nobody has any other questions there. And so this quiz will probably pop up one more time sometime within the next few weeks. Mike was trying to pin me down to it, but I told him I don't give them any decisions on Monday mornings. I don't make decisions on Monday mornings. So.
Mondays or Fridays, you mean?
Mondays or Fridays, and then typically no any of the days in between there either.
Yeah.
Anything that ends in Y, right?
Yeah, that's right. Anything that ends in Y. All right, chapter 10. Chapter 10 is it? Other than it's a lot of little new math here. All right, so to practice using our math, I got some math worksheets here. You can kind of, I'll open this up here real quick. And you guys seen too, the nice person I am too, I gave you all the basic AC equations that we're going to be using here from now on throughout the rest of the course here. Or not, yeah, the course ends through this semester here. There's only, there's one formula that isn't on here. And I'll tell you that when we get into the RLC circuit, the resonating frequency formula isn't on there. And I'll warn you again on chapter 14's quiz that it's not on there, and to make sure you write it down on your, make sure you memorize it.
Well, we can't use this sheet for the quiz?
Well, you can use this sheet, though. This sheet can be used on the quizzes now. So you always can have this sheet, so I'm not going to make you memorize all these quizzes.
Oh.
But there is one formula that's not on here that you're going to have to write on there yourself.
I think it's this last night going,
And I always hate you if we had to do that. And I always die laughing because somebody will get that, they'll get their final, and they'll start working, and they'll see the circuit, and all of a sudden you see them going, and they'll start, what is that formula again? But I'll tell you when we get to that formula, I'll tell you when to write that down on your sheet there. So, yep, so this one here you can use on all your quizzes and finals and stuff like that. I won't make you rewrite these ones down. All right. So let's take a look at our practice using our calculators. Find your manual for your.
No, I haven't.
All right, so when we get into what we call RC circuits, meaning that there's going to be a resistor and a capacitor in our circuit, strange things happen. It's not, we can't just add everything up algebraically. We got to use it through trig and stuff. Now, Ohm's law will still apply when we're talking about at our component level, but doing all our total calculations and everything is going to be done with using trig. And what we're going to be doing is we're going to be using vectors. So if you work with vectors, then you know that we have a quadrant 1 here, quadrant 2, quadrant 3, and quadrant 4. And each one of these quadrants then is also going to be represented by a certain amount of degrees. So we're going to have 0 degrees here, 180 degrees here, 270 degrees here. Oh, that's what it said. Oh, 90. I've got 90. Sorry. 90 degrees, 180, and 270 degrees. So in our little math worksheet, we're going to be using all 4 quadrants. But once we get into using it in our actual circuits and stuff, the only 2 quadrants that we're ever going to be in is going to be quadrant 1 and quadrant 4. So then also, the little one does it can represent what the angle is. We can also do what we call our rectangular functions, which is, this is going to be, you know, my x value, this would be my plus x value, my plus y value,
Oh, yeah.
my negative x value, and then
I saw that.
my negative y value. What's that?
I was reading your sheet this morning, or last night, and I
Yes.
just read the highlighted section on here.
Oh. Yeah, I had an older student in the class, and his wife, I'd just be dying in that house, but his wife would just be hounding him. Well, did you get your schedule for next spring? We got to get you signed up for all this, you know. And so he'd come every day, he'd come and hound me, and I said, well, you can't register yet anyways, the dentist, you know, you got to wait and stuff. Well, my wife is all over me to get to get our schedule and stuff. And so I finally filled it out for him, and then I wrote that on the top of him for turning to give it back to his wife and stuff. All right, so these are going to be our quadrants that we're going to be working in. We're going to be working with our x and y values. So if I know, for example, like if I know I have a certain x value, so for example, let's say I got 1, 2, 3, 5. There, we got about 10. We'll just say that, you know, if I know that I had an x value of 5, which is this one right here, and a y value, a positive y value of 5, so somewhere about here, I would end up drawing a dot in there. I would put a dot where those two numbers intersect. So I'd have so what I would represent this would be, I'd have a plus x equal to 5 and a plus y equal to 5. And I'm going to get a location in my vector here. And then this is going to be my resultant when we're working with our thing. This is going to be our total voltage, our total impedance, the total total current, whatever it is that we're looking at. And that's going to be the length of this line is going to determine what that length is. Whatever that length is going to determine what our total voltage is or whatever it is. And then within that, then there's also going to be, we're going to also know what the angle is. So for example, this one here, this is going to be our Z. This plus X is going to be our resistance. And then since I'm up in Y quadrant, this is going to be my X of L, so that's going to be my inductance. So I know I'm going to have a certain amount of inductance going across my inductor, I'm going to have a certain amount of resistance going across my resistor, and the total of those is going to be my total impedance, or my total resistance of that circuit. And that length, we're going to be able to calculate out that length using our calculators. And that's going to be our total length of that, that's going to be what our total is. And then, just like when we were talking about capacitors, remember when we were looking at the capacitors, remember my current and my voltage aren't within phase of one another. Okay? And this will determine what is that phase shift. So, for example, whatever that voltage is, I might, this length of this long length here, my resultant, is going to be my total voltage source. Here is going to be my total voltage across my resistor, and this will be my voltage across my inductor. My voltage across my inductor is going to be leading the voltage across my resistor by 90 degrees. And then my voltage source, my voltage across my voltage source is going to be somewhere between my voltage of my resistor and my voltage of my inductor. But you'll see that once we, get doing the worksheets and stuff like that. And so this is how we're going to do this is how we're going to have to add up all our totals and stuff like that. We're going to have to do everything kind of vectorally. So before we get into that, though, we're going to we'll practice using our calculator so everyone knows how to use their calculator. There's two different types that we're going to be working with. We're going to be working with it either in the rectangular formula, meaning that I know my x and my y, or we're going to be working with my polar formula, where I know my resultant, which is this, the length of this line, and I know my angle. And then I can calculate out what my x and y would be based off of that. So now I handed you another sheet there that kind of helps us out with our calculators. I can take a look. Everyone got their chapter 10 stuff, right? All right, come on over to the lab and grab it.